the nucleus of the atom is positively charged, the electron is negatively charged. Yes, so they are oppositely charged. What will be happening there? Attraction, right? So if plus and plus are overlapping, that means the same phase is overlapping. That means a positive overlap is obtained. The overlapping is comparatively less than the sigma bond. So overlapping is less means the bond strength will be also less. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. Last class, we discussed about the valence shell electron pair repulsion theory, right? Where in detail we studied about the geometry of molecules with only bond pairs. Yes, and then we discussed about the geometry and shape of the molecules with bond pair as well as lone pairs. Right? And then finally, we even discussed about the limitations of VSEPR theory. Right? So, in today's session, we will be discussing on the next approach to chemical bonding, that is valence bond theory. Right? We are going to discuss about valence bond theory, in which we will be studying about the directional properties of the bonds and the types of overlapping and the nature of covalent bond in this session. Right? So, we are beginning with the next approach to chemical bonding, that is valence bond theory, or in short form, you can also write it as VBT. Right? So, till now, we have discussed about the Coastal-Lewis approach and the VSEPR theory. Right? So, according to VSEPR theory, yes, what did we discuss? Yes, the VSEPR theory could predict the shape of the molecules, right? Yes, based on the repulsion between the electron pairs, the shape of the molecules could be predicted, right? And when we were discussing about the limitations of VSEPR theory, it was mentioned that VSEPR theory was not based on the quantum theory, that is quantum mechanical model of atom, right? It was not based on the quantum theory. Right? It was based on the Bohr model of atom. That is, electrons will be revolving around the nucleus in fixed paths. Right? In circular paths called orbits, the electrons are revolving. It was based on that. But the valence bond theory, yes, it is based on the quantum theory. That is, what did we study according to quantum mechanical model of atom in the last chapter? Yes, it is that electrons are present in the atomic orbitals, right? Electrons are present inside atomic orbitals. Yes, we know that there are shells in which there are subshells and inside which orbitals are present, and inside the orbitals electrons are present. All this we already know. Right. So, according to the quantum theory, yes, electrons are present in the atomic orbitals. Right. It is not a circular path. It is a region wherein which the probability of finding electron is maximum. Right. So, the valence bond theory is according to the quantum theory. That is what you have to understand in the beginning. Right. Yes. So, it was introduced by Hitler and London in the year 1927. Right. And it is based on the concept of atomic orbitals and electronic configuration of atoms. So, in valence bond theory, we will be considering atomic orbitals, right? Not the orbits, we will be considering the atomic orbitals here, right? Now, according to this theory, a covalent bond is formed between the two atoms by the overlap of half-filled valence atomic orbitals of each atom containing one unpaired electron. So, what do you understand from this sentence? Yes, how a covalent bond is formed here? Yes, according to this theory, a covalent bond is formed when two atoms are coming together, right? What do we understand? When two atoms are coming close and close to each other, yes, the electrons where it is present, yes, it is present inside the atomic orbitals, right? So, what happens is each of these atomic orbitals will be having one unpaired electron, right? Let's consider one atom here and one atom here. Yes, I have represented the two orbitals here. Okay, this one will be having one unpaired electron and this one will be having one unpaired electron. Right, now when the atoms are coming close and close to each other, what happens? This atomic orbitals overlap with each other. Right, they come so close to each other that they overlap with each other, and then what happens? These unpaired electrons will be paired. That is, these two electrons will pair up now. Clear? So this is what is happening according to valence bond theory. That is, when atoms are coming closer to each other, yes, what happens? The overlap of half-filled valence atomic orbitals take place. Right? These two orbitals overlap with each other and each of this will be half-filled. Right? Yes. And what happens? And each of these orbitals will be containing one unpaired electron. Right? And these come together, they overlap and they pair up. This is what is the valence bond theory is about. Right. Now, let's try to understand it, what exactly is happening here. Yes, you might not be that clear with the concept of atomic orbitals coming like overlapping. Yes, let's understand it with the example of hydrogen itself. Right. So, now what we are going to do is we are considering two hydrogen atoms A and B. Right. So, now we are considering two hydrogen atoms, hydrogen atom A and hydrogen atom B. Okay, so what is Na and Nb? Na is the nucleus of atom A and Nb is the nucleus of atom B. Right, and we know that electrons will be present here, and the electrons present in the atom A is represented as Ea and electrons present in here are represented as Eb. Yes, till here it is clear? Right. Now, what happens is, as you can see, two atoms are here. Right? The nucleus and electrons are represented here. So, now you can see here, when they are coming close together, right, there will be attractive forces as well as repulsive forces happening. Right? Where? See, the nucleus and the nucleus. So, first let's discuss about the attractive forces that will be happening in between these two atoms. So, the first one will be the nucleus of one atom and its own electron. See, the nucleus of the atom is positively charged, the electron is negatively charged. Yes, so they are oppositely charged. What will be happening there? Attraction, right? So there will be an attraction between the nucleus and the electron of A atom and nucleus and the electron of B atom, right? There will be attractive forces, that is NaEA, between NaEA and between NbEb. That is nucleus and electron of the same atom, there will be an attractive force. Now, there is one more attractive force that is possible when these two atoms are coming together. Yes, nucleus of one atom and the electron of the other atom. That is, when they are coming close together, yes, the nucleus of A atom attracts the electron of B atom, right? And the nucleus of B atom attracts the electrons of A atom. I hope that is clear. So, these two attractive forces are acting there. Now, coming on to repulsive forces, right? So, what are they? The electrons of two atoms, they repel each other. See, the same charges, they repel each other, right? Both of the electron cloud will be having negative charge. Yes. So, this electron and this electron will repel each other. Right. Now, one more repulsive force will be there, which is it? The nuclei of the two atoms. That is, now the nucleus, both are positively charged. Right. So, these both nucleus will repel each other. So, I hope this part is clear. That is the attractive forces and repulsive forces that is acting when two atoms are coming close together. So, till here it is clear. So, as you can see here, yes, this dotted lines which are shown here are already existing forces there, that is all old forces, and these bold lines shows the new forces, right? So, Na and Ea, that is between the nucleus of the A atom and the electron of the A atom, already there will be an attractive force that is happening, right? Before itself it was there. But when the atoms are coming close together, now Na and Eb will be also having an attractive force. Clear? Now, that is why it is represented by bold line. Right. Now, the attractive force between Nb and Eb was already existing. Right. It is between the nucleus and the electron of the same atom. Right. Now, between Nb and Ea, it is a new attractive force that is present there. Clear? Yes. So, I hope it is clear the attractive and repulsive forces that is happening here. Now, what you have to understand is, Yes, experimentally it was found that the magnitude of attractive force is more than repulsive force. Right? So we understood that attractive force as well as repulsive force is acting when two atoms are coming close together. So it was experimentally found that the attractive forces are more than the repulsive forces. So what does that mean? Now the atoms will again come closer and closer to each other. They won't be repelling because the attractive force is more. So atoms will be coming more and more close to each other. Right? And what happens? Ultimately, a stage is reached, right, where the net force of attraction balances the net force of repulsion and the system acquires minimum energy. So what happens? The atoms keep on coming closer and closer to each other, and finally at a point, yes, the force of attraction and the force of repulsion becomes equal. Yes, at this stage, the system acquires minimum energy. Right? If the system is acquiring minimum energy, that means now it is highly stable. Minimum energy means maximum stability, right? At this stage, the two hydrogen atoms are said to be bonded together to form a stable molecule. So what you can understand here, at this stage, as said, yes, there will be minimum energy. That means maximum stability, right? So at this stage, what you can observe is, yes, they have come so close to each other that, yes, their atomic orbitals have overlapped. Yes, why is this? Because at this stage, the attractive force and repulsive force, yes, they have become equal and the energy is less. That is represented in this diagram, right? Finally, what happens? The energy will be least here. That means maximum stability, and that will be the most stable state where the chemical bond will be formed. Right? Now, the bond will be formed between the atoms by the overlapping of this atomic orbitals. So, at this stage, what you will be able to observe is that the atomic orbitals of the first and the second atom have overlapped with each other. Right? And this way, atoms combine and form molecules, or we can say that now the atoms have combined and formed a stable covalent bond. I hope it is clear. Right. Now, in the formation of hydrogen molecule, right, there is a minimum energy state when two hydrogen atoms are so near that their atomic orbitals undergo partial interpenetration. Yes, that is what we discussed now. Yes, at this stage, when the minimum energy stage is attained, now the atomic orbitals will be overlapping with each other. That is, partial interpenetration will be happening. For that, we say that atomic orbitals are overlapping with each other, right? And this partial merging of atomic orbitals is called overlapping of atomic orbitals. So this partial interpenetration is called as overlapping of atomic orbitals. Clear? Which results in the pairing of electrons. So what does that mean? Yes, this one orbital was having one electron, unpaired electron, and the second orbital was having another unpaired electron. Now what happens? Yes, what happens when they combine each other? Now it gets paired. Right? So greater the overlap, stronger is the bond formed between the atoms. Now what you can understand from that? Yes, when the extent of overlapping is increasing, the bond strength also increases. Now let's say these are the two atoms. When they are standing just like this, yes, the bond strength will be quite less. Now if they are again overlapping a little more, they are coming little more closer. What happens? Yes, the bond strength will be more here. And finally, if I am saying, if the atomic orbitals have overlapped to this much extent, yes, this much they have overlapped with each other, that means the bond strength will be the highest, right? It will be that difficult to break it up, right? Yes, so that means in a way we can say that when the overlap is to the greatest extent, the bond strength will be more and the bond length will be the least. Even that way also you can say. Yes, so I hope the overlapping concept is clear for you, what exactly or how exactly the atomic orbitals are overlapping and forming a chemical bond. And thereby the atoms combine and form the molecules. Yes, it is clear. So now moving on to the next part, we are going to discuss about the different types of overlapping that is possible. Right? We understood how the atomic orbitals will be overlapping. Now we are going to discuss about the different types of bonds, that is different types of overlapping that is possible, and the directional properties of the bonds we will be discussing here. So the factors determining the overlap. So which type of overlapping is possible? right? Based on which factors they are depending? It is phase and orientation. Yes, if both the atomic orbitals are having same phase and same orientation, yes, a positive overlap will take place. That's the first type. That is a positive overlap. That is if same phase and same orientation. So as you can see in this particular diagram, right, two orbitals, they are in the same orientation. Yes, they are coming in the same direction and they are having the same phase. Now what is phase? Yes, you can see the plus and minus sign that is shown here, right? Let's assume this one as one orbital and this as another orbital. Okay, now they are coming in the same direction. Now as you can see, minus, plus and plus minus, this plus and minus is showing the phase of the orbital. So if plus and plus are overlapping, that means the same phase is overlapping. That means a positive overlap is obtained. So as you can see here, yes, they are in the same phase, right? So this is an example of positive overlap, right? Now what about this case? As you can see, this is a spherical shape. That means it is s orbital, right? And the dumbbell shape is for p orbital. Now an s and p orbital is overlapping. See, as you can see here, both it is plus sign. That means they are in the same phase, right? Now that is positive overlap. Now what is negative overlap? Yes, when the phase is different, that is, yes, one will be positive and one will be negative. So you can see here, right? Yes, in the first orbital, the positive phase is overlapping with the negative phase of the other orbital, right? And in this case also, you can see that, right? Now that is negative overlap. Now one more thing is there, that is zero overlap, where overlapping is not even taking place. Now what is that? So as you can see in this case, right? Here what you can see, the overlapping is not taking place. Why? See, a p orbital is present here. Yes, the phase is also mentioned and there is an s orbital here. Okay. Now what happens, even though it is coming closer to each other, yes, overlapping is not possible here, right? Why overlapping is not possible, right? Because the electrons are actually present here and here on the lobes. We know that. So if the overlapping has to take place, this s orbital has to combine either from here or here, right? And it can't come in this direction. So the overlapping won't be taking place. Right, that is one example. And in this example also you can see a p orbital is here. Yes, and another p orbital is in another orientation. Yes, the direction is different now. So if they are coming close to each other, will they overlap? No, right? If the p orbitals have to overlap with each other, as you can see here, it will be like this. Right, it will be overlapping sideways. Yes. So, as you can see here, it will be like this or it can be like this. Either way, the direction is same. That is, the orientation must be same. If in this case, the orientation itself is different, that means overlapping is not possible. So, these are the three types. That is positive overlap, negative overlap and zero overlap. Right? Now, based on the different types of overlapping, different types of covalent bonds are formed, which we will be discussing now. So, the two types of bonds that you can see here is sigma bond and pi bond, right? Sigma bond is represented by the sign sigma and pi bond by this sign, right? Yes. Now, how is sigma bond formed? Let's see. It is formed by the end-to-end overlap of bonding orbitals along the intermolecular axis. Now, what is sigma bond? That is, it is formed by the end-to-end overlap. As you can see here, in sigma bond itself, we will be studying SS overlapping, SP overlapping, right? SS overlapping, SP overlapping and PP overlapping we will be studying. So, what is happening here is, yes, they are overlapping in an end-to-end, or you can say that it is head-on overlapping. Yes, as you can see, the first type is SS overlapping. That is, one s orbital is here, one s orbital is here, and each of them will be having half, it is given, two half-filled s orbitals overlap along the internuclear axis. That means one unpaired electron is present in this s orbital, another is present in this orbital. Now, what happens? They overlap with each other. That is head-on overlapping is happening. That will happen along the internuclear axis. Yes, internuclear axis is then axis which is passing through the nucleus of both of these orbitals, right? So, what happens here? The two orbitals, yes, they overlap with each other. Yes, as you can see here, now the two electrons will be paired. Now, this is called as SS overlapping. Now, coming on to the next one, that is SP overlapping. So, from the name itself, you can suggest, yes, an S orbital and a P orbital will be overlapping with each other, right? Even this, what is happening? Yes, it is head-on overlapping. It is an example of sigma bond, right? Yes, it is formed by the overlap of half-filled S orbital of one atom and the half-filled P orbital of another atom. As you can see, this is the S orbital and this is P orbital. Right. Now, along the internuclear axis, yes, they are head-on overlapping. That means this part is the head here and this is S orbital. So, it is already spherical in shape. Now, they will head-on overlap. That is what you can see here. The P orbital and the S orbital head-on overlaps with each other, or you can say end-to-end overlapping takes place here along the internuclear axis, and the one unpaired electron here and the one unpaired electron in the P orbital, they pair up now. Okay, so you can say a sigma sp bond is formed here. Clear? A sigma bond is formed here because of the head-on overlapping. Now moving on to p-p overlapping. A p orbital and a p orbital is head-on overlapping, right? So it is formed by the overlap of two half-filled p orbitals of two atoms, right? A p orbital of one atom and a p orbital of another atom. They are head-on overlapping. Yes, along the internuclear axis, they are overlapping. So as you can see here, this type of overlapping take place, and the unpaired electron present in each of this orbital now pairs up, right? And a sigma pp bond is formed here. So these are the three types of sigma bond which is formed. Now moving on to the next one, that is pi bond. Now what is pi bond? It is formed by the sideways or lateral overlapping of atomic orbitals. And atomic orbitals overlap in such a way that their axes remain parallel to each other and perpendicular to the internuclear axis, right? So in sigma bond, the orbitals were overlapping along the internuclear axis, right? But in the case of pi bond, the atomic orbitals will overlap sideways. As you can see, there is a p orbital here, p orbital of another atom here. They sideways overlap. Yes, as you can see, this is one and this is another one, right? They are sideways overlapping. Yes, if it was in this direction, see, if the same p orbitals were in this direction, that means the head-on overlapping will take place. Now that will be a sigma bond which is formed. But now it is lateral overlapping. That forms pi bond. So I hope you are clear with the difference between sigma and pi bond. It is lateral, or you can say sideways overlapping of atomic orbitals, or it can be also represented in this form, right? Along the internuclear axis, yes, on top of that and below that, the two orbitals will be present. Clear? Yes, that way also you can represent it. So, the two axes remains parallel. That is, the axis of these two p orbitals will remain parallel, right? The axis of this p orbital is here and this p orbital is here. They will remain parallel and it will be perpendicular to the internuclear axis. That is, it will be perpendicular to the internuclear axis. Yes. So, now the question arises whether sigma or pi bond is stronger. Yes, we understood how sigma bond is formed and how pi bond is formed. Now, out of sigma and pi bond, which will be stronger? Okay, let's take the example and see. In the case of sigma bond, let's consider these two p orbitals. Right? How is a sigma bond formed? By the head-on overlapping of the pp orbitals, right? It can be sp, pp or ss, right? So, I am considering two p orbitals here. So, they are head-on overlapping. What happens here? Yes, as you can see, yes, here they overlap with each other and a bond is formed here. This is in the case of sigma bond. Now, if a pi bond is formed, it is like this, right? It is sideways overlapping. See, this is sigma bond which is formed here. and this is a pi bond which is formed here. Now from here itself you can understand which one will be stronger. Yes, here the extent of overlapping is more. Right, it is head on. That means the extent of overlapping is more here. But consider in this one, it is sideways overlapping, means a very little area is only getting overlapped. Right, the extent of overlapping is less in this case. That means, what did we study in the beginning? If the extent of overlapping is more, yes, greater will be the strength of the bond, right? So in this case, as more amount of, or as you can say, greater the extent of overlapping is taking place here, that means sigma bond will be always stronger than pi bond. Clear? Yes, because in here the overlapping is comparatively less than the sigma bond. So overlapping is less means the bond strength will be also less. So sigma bond will be always stronger than pi bond. Now, where actually can you observe these sigma bonds? Yes, wherever single bonds you can see. Yes, you are familiar with single, double and triple bond, right? So wherever single bond is present, yes, there will be a sigma bond, right? So that is also clear. Yes, so let us summarize all of which what we have studied now. Yes, sigma bond and pi bond. Yes, sigma bond is formed by the axial overlapping. Yes, it is happening along the internuclear axis, right? Or it is also called as head-on overlapping. Now, what about pi bond? It is formed by the sidewise or lateral overlapping, right? Now, sigma bond can be SS, SP and PP overlapping. Yes, in the case of pi bond, only PP overlapping is possible, right? S orbital, we know it is spherical shape. So, sidewise overlapping is not possible there, right? It is spherical in shape means, yes, where it can be the sideways overlapping possible here. In the p orbital only, sidewise overlapping is possible. Clear? Now, in the case of sigma bond, the overlap is large and hence the bond is strong. That is what we discussed just now. And the overlap is small and the bond is weak in the case of pi bond. Now, in the case of sigma bond, it is always single bond, right? And yes, pi bond will be the ones which is forming the multiple bonds. So, wherever you can see the multiple bonds, it will be, yes, a single bond and then multiple bonds will be present, right? So, the pi bonds will be present in the multiple bonds, right? And free rotation about sigma bond is possible. So now free rotation about sigma bond is possible. Now what is this? Yes, as you can see, sigma bond means it is single bond, right? So a single bond, the strength will be, yes, this bond strength will be more. So that around the internuclear axis, yes, the rotation is easily possible. But in the case of pi bond, the free rotation is not possible. So you know that, yes, multiple bonds are present there. Right, multiple bonds are present there means the atom won't be, that is the atoms which are bonded to these multiple bonds will not be able to rotate freely. Right, here if only one single bond is present, yes, let's say, let's consider this particular molecule. Yes, if only one single bond is present, that is sigma bond. Yes, along this axis, if I want to rotate this CH3 part, yes, it is easy. Right, only one single bond is present here. But let's take the case when a triple bond is present here. Right, so free rotation is little difficult in this case. Right, why? Because, yes, it is triply bonded. So, the rotation along the axis will be quite difficult rather than in sigma bond. That is why free rotation about the sigma bond is possible. But in the case of pi bond, it is not possible because it is triply or doubly bonded. Right? So, I hope till here it is clear. So, in the next session, we will be discussing further about the next topic, that is hybridization, which is very, very important, and will be also discussing about the different types of hybridization. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.